Now in the videos that follow, we're going to talk about how to find activation barriers, and we're going to talk about how to find rate constants and things like that. And I wanted to put a little bit in here to let you understand that we are kind of looking at a really oversimplified idea here. Reason I tell you that is that when we measure an activation barrier and we call it an activation barrier, we call it an activation energy, we're actually leaving off a very important word. And the really important word is apparent activation energy. So in a previous video, I showed you H2O plus O2 goes to H2 plus O2 goes to H2O, and I showed you there were two transition states in the overall reaction. Well, experimentally, we can't measure both. There's no way to do that in a reactor because the intermediates are so short-lived, we couldn't feasibly stop the reaction. And the only way to find those actual individual activation barriers is to do a lot of computer modeling, and even then it's not going to be that reliable. So we have an activation barrier for it. What is it representing? Well, the slowest reaction, so the highest barrier is the slowest reaction. So of all your steps in your reaction mechanism, the one that has the highest activation barrier is the bottleneck, and this is what's called the rate limiting step. It literally limits the rate of reaction, and it is the step that does this. So when we measure an activation barrier, we are typically measuring the activation barrier for the RLS, or rate limiting step. Now what we call this in actuality is what's called the apparent activation barrier, because if you've got enough energy to cross over the activation barrier for the highest peak you got to go over in that reaction mechanism, then you've got more than enough to cross over all the other little ones. And so even though we're measuring an activation barrier, it doesn't include all the ones that are beneath it. So it's considered apparent because it's apparently the only one we can measure. Now, the other thing to keep in mind when we talk about activation barriers is that it's kind of an art to do these things experimentally. So a lot of the problems you're getting are really cooked problems. They're not this practical in real life. Now, the only other thing I really want to caution you about is that we love power laws, and we love using power laws for rates because they're so easy to understand and they're so easy to work with. 99% of the reactions in this world do not use power laws. We use power laws because they are easy to find the coefficients for. It's easy to find K, it's easy to find all the powers of the concentrations. If you take a biology class though and you go into reaction kinetics, you're going to see something called the Michaelis-Menten equation. It's derived. There's a proof for it. It does a really good job and it looks nothing like a power law. So don't get into this idea that power laws are everything. They are actually a very limited case of power laws. Now the 152 level, this is all we cover, it's all you need to know. But realize that there's a bigger picture out there. And what I'm showing you, what I'm arming you with are the tools to go out there and solve the bigger problems. So that said, let's carry on with some videos. Let's try to find an activation barrier. Let's try to find the coefficients inside a power law relationship based on the concentrations. And also let's look at concentration versus time to see if we've got a first order, second order, or zero order reaction.